In this video, we are going to continue our discussions of angular momentum by talking about conservation of angular momentum. The idea that momentum, even if it's angular, can't just randomly disappear or be generated. The fact that within isolated systems, it is going to remain constant. So the main focus of this video is going off of the idea that we developed in the last video, where if there is an isolated system, or for rotational motion, if there are no external angular impulses acting on the object, so that means no torques acting on that object for a time period, then that means the total amount of angular momentum in a system is going to remain the same. So that means if you set something spinning and there's no external torques, it's going to continue to spin at the same rate. But then we also have this idea of internal interactions. So if we have this cat chair system, they are pushing against each other. We have this overall net internal interaction between the cat's paws and the chairs. But notice overall, there is no change in the rate that this chair cat system is rotating. The total angular momentum is remaining constant. So we are mainly going to be focusing again on systems where the overall momentum will not change. And the idea that the angular momentum of a system is going to be constant has a really interesting application for rotational objects, because the moment of inertia of an isolated system actually can change. So if we think about, say, the moment of inertia of these spinning Olympic divers right here, there are things about the system that we can change. Now, we're not going to change the mass. The total number of particles in these divers are going to stay the same. But what we can change is the shape and the mass distribution. What we can do is we can pull mass in tighter or change the way it's distributed within a system, and that will overall change the moment of inertia of a system. So if this is happening to an isolated system, so once these divers are up in the air, they are going to be isolated, there's going to be no net torques acting on them, then that means the initial angular momentum that they start with is going to be the same amount of angular momentum that they end up with. There's no net external torques on this system. So their initial angular momentum is going to be their initial moment of inertia times their angular velocity. And what is going to be interesting is when they begin their dive, what they do is they tuck their body into this really tight position. They essentially decrease their overall radius of their body, which is going to decrease their moment of inertia. So we are going to see a smaller moment of inertia when they tuck their bodies. Now, in order to keep this equation true, if we decrease our moment of inertia, then that means our angular velocity has to increase. These divers are going to begin to spin faster and faster, and that's how they get this really tight spin. It's because they have tucked their body into themselves and decreased their radius. So as long as the angular momentum remains constant, as long as we have no net external torques, if the moment of inertia decreases, then the angular velocity will increase. The same thing is true in the opposite direction. So when they want to leave this dive right at the end, what they do is they unfurl their body, they increase their radius, and then they end up decreasing their angular velocity so that they can basically stop spinning and enter the water smoothly. So this is a really interesting application because you can essentially change the rate at which you are spinning by simply changing how your mass is distributed. Figure skaters do this. This is one of their natural skills to get faster and slower spins. So as long as they are isolated, so they're going to be on frictionless ice, if they want to spin slow, they're going to stick their arms out. They're going to have a higher moment of inertia because they have a larger radius, so they are going to spin at a slower angular velocity. But if they tuck their arms in and they decrease their radius, they're going to decrease their moment of inertia and increase their angular velocity. So they do that when they're spinning on the ice, but they also do that when they are doing their jumps. But once this person stands up, they tuck their arms in, and you can see that they spin really, really quickly. Then in order to stop, they furl their arms out, and they end up moving slower. So they can control the rate of their spin by basically changing how their body is oriented. And then this demonstration is one of my favorite examples. So this is a toy that you might have had as a child. It's basically a sphere that collapses in and out on itself. But we can see it is rotating with some initial angular momentum. And when the ball is very large, when there's a very large radius, it is moving very slowly. And when he tucks all that mass in on itself, when he decreases that moment of inertia, decreases the radius, gets all the mass very centered to that axis of rotation, you can see that angular velocity increase at a very fast rate. So when it's out in this big configuration like that, we have a really large moment of inertia, small angular velocity, and when it's tucked in like this, we have a very small moment of inertia, so a very large angular velocity. So let's look at some examples. A boy is standing near the center of a frictionless merry-go-round on a playground. So that's going to be one of these things that spin. As it is spinning, he is going to begin to walk towards the outside of the circle. Describe what happens to that frictionless merry-go-round and why. So the first thing that we should notice is that this is going to be an isolated system. It is specifically frictionless, so there is no net external torque on this system. So that means the angular momentum that this starts with is going to be the same as the angular momentum it ends with. This disc boy system has a certain moment of inertia because he is near the center, and then it's also moving at an angular velocity. So as he begins to walk towards the outside of the circle, we have to think, what is changing? What is happening to the moment of inertia of this system? So overall, notice mass is not changing. It's still the boy. It is still the merry-go-round. The radius is also not changing because the merry-go-round has a fixed radius. He's not expanding this disc to a larger size. But what is changing is the mass distribution. Notice a lot of the mass of this boy, as he walks towards the outside, he is moving the mass further away from the axis of rotation, which is going to be right in the center. So for the moment of inertia, what we are changing is this K value. We are increasing it because the mass is moving further away from the axis of rotation. As we increase our moment of inertia, that means this merry-go-round is going to spin slower. It is going to slow down in order to conserve angular momentum. In the second example, this is going to be a math-based example. We have a skater that is spinning at 32 radians per second with her arms and legs extended outwards. In this position, she has a very large moment of inertia. It's going to be 45.6 kilogram meters squared. She then pulls her arms in, tucks them in like I showed you, close to her body, and now her moment of inertia has decreased significantly to 17.5 kilogram meters squared. So we want to calculate her new angular velocity. So we have to start with a basic equation, a basic idea. But since this is an ice skater spinning on ice, we can definitely say that this is an isolated, no external torque situation. So I'm going to say her initial angular momentum is going to be equal to her final angular momentum. For this problem, they've basically fed us all the values we need. I just want to do a quick check of the units, radians, kilograms, meters. That's good. So she initially has a moment of inertia of 45.6 kilogram meters squared, moving at 32 radians per second. So we're going to get an initial angular momentum of around 1,459 kilogram meters squared per second. We're going to set that equal to her final angular velocity times her moment of inertia. So I'm going to divide both sides by 17.5, and I get a final angular velocity of around 83 radians per second. Notice her moment of inertia decreased, so her angular velocity should increase. Now, within these problems, we saw that the total amount of momentum in the system remained the same because it was isolated. But one thing that we learned when we were looking at translational momentum was this idea that even if the total momentum of the system overall remained constant, the way that that momentum was arranged within that system could change due to these internal interactions. So if I had these two balls collide, overall the momentum is going to be the same. But this ball on the left might experience a change in momentum of negative 30 kilogram meter per second. And that would mean the ball on the right had to gain 30 kilogram meter per second of momentum. So that overall, the net change was 0. We saw within these interactions that these changes in momentum within the system are always going to be balanced. Well, the same thing is going to happen for angular momentum as well. So if I return to this boy on the spinning merry-go-round on the playground and he moves to the edge of the playground, there are some ways that we can look at this. So if we look at it as the entire person disc system, again, this is going to be an isolated system. There's no friction between the disc and the ground. And even though there is an interaction between the boy's feet and the top of this merry-go-round, this interaction is internal, so it's not going to change the overall angular momentum of the entire system. So we have the total angular momentum of this system is going to remain constant, even though we have this change in mass distribution. And again, the main reason why is because this frictional contact torque between the person and the disc is internal. It does exist, but it's not going to change the momentum of the system as a whole. But what if we look at the merry-go-round and the boy as two separate systems? What would we be able to see? Well, if we look at the disc itself, as the boy walks to the outside, we know that the entire system is going to slow down. So that means the disc itself is also going to slow down. Its angular velocity decreases. That means that it is losing angular momentum because notice the moment of inertia of the disc itself hasn't changed. And since it lost angular velocity, it had to lose angular momentum. Now, the person walking on the disc is also going to slow down, but their radius is increasing. Their moment of inertia is increasing, and that radius actually matters so much because this r is squared in this equation. So even though their angular velocity is decreasing, their moment of inertia is increasing so much that overall they are going to gain angular momentum. And it's actually true that the amount that the disc loses, the person is going to gain. This internal interaction between the person's feet and the merry-go-round is going to basically take away momentum from the disc and give it to the person. But these changes are going to balance each other out. There is no overall change, but the disc is going to lose angular momentum while the person gains it. So always keep in mind how the system is being defined. Are they having you look at an overall isolated system, or are they having you look at two individual objects that make up a bigger system? So a final application of conservation of momentum that we haven't looked at yet is going to be the momentum of orbiting objects. Because if I have a planet that is maybe orbiting a central sun, this thing is in rotational motion. It is spinning around a central axis. Sometimes that orbit might be circular, sometimes it might be elliptical, but we can still look at the same type of analysis. So let's look at the angular and linear momentum of just the planet as our system, and that is orbiting a central sun. So the first question is, will the linear momentum of this planet change? Well, the first question is, when are we going to have linear momentum change for an object? Well, the linear momentum is going to change when there is a net external force on the object. Well, if our system is just the planet, there definitely is a net external force. This sun in the center is exerting an external force of gravity that is definitely applying an impulse. So the linear momentum of these objects are definitely going to be changing because we have this net external force from this planet. But what about the angular momentum of these planets? Will the angular momentum change as it orbits around this central sun? So to answer this, we have to think, well, when will we have a change in angular momentum? Well, angular momentum will only change when there is a net torque on the object. Now notice, we have a net force, but this net force actually does not exert a net torque. And that's because the center of this object's rotation is going to be this central planet. And the force of gravity exerted by this central sun is always going to point exactly towards that sun. Notice this external force is always directed through the axis of rotation. So even though there is a net force, there is no net torque. So the angular momentum of this planet actually will not change. It is going to remain entirely constant. The linear momentum will change, but the angular momentum will not. But we can also look at this as a two-object system, so the central planet and the outer planet. And in this situation, angular momentum still will not change because this force still acts right through the axis of rotation. But once we make this force of gravity internal, now linear momentum of this two-object system will not change. This internal gravitational force between them are again internal, so it is still an isolated system, so the overall momentum will not change. The momentum of the planet will change, but so will the momentum of this inner planet. Essentially, the central planet does wobble back and forth a little bit, and all of that motion balances the change in motion of the outer planet. We obviously can't see these planets wobbling, but this is a good GIF that kind of shows what is going on. As this outer planet is making its revolution, we can kind of see that the center planet, let's pretend that there's a central planet here, is also wobbling around and is moving to kind of counteract the external motion of this outer planet. So this is an isolated system. Neither angular nor linear momentum will change as long as we're looking at both of these together. If we look at just the train or just the track, then suddenly it's non-isolated. So in summary, angular momentum is going to be constant when there is no net torque on the system. This has this interesting application here, where as long as we're not changing the overall angular momentum of the object, if we adjust the moment of inertia of the system, then the angular velocity is also going to respond. So if we increase the moment of inertia, we will see a decrease in angular velocity and vice versa. And then the next big idea, if there is a net torque on our system, that will change the angular momentum. So if I wanted to overall stop this thing from spinning, I would have to stick my hand in it and apply a net torque. And then finally, we have this application. It tends to show up a lot in multiple choice problems, but for orbital motion, angular momentum is always conserved. It does not matter how we are defining this system, whether it's just a single planet or if we are doing the planet-sun system, angular momentum will always be conserved and specifically constant. That is because the force of gravity is always going to act right through that axis of rotation. Linear momentum, however, does depend on the system definition. So if we are just looking at the planet, then the force of gravity is suddenly external, and that's going to exert a net force. But if the system makes that force of gravity internal, then there's no net external force, and linear momentum will remain constant. So just keep these ideas in mind for orbits, for potential multiple choice questions. But the big idea, angular momentum is always going to be constant.